All right, legends, this is Mr. Maze coming to you through the digital space. Welcome to Unit 9. Yes, we have made it to Unit 9. And Unit 9 is just made up of sort of a hodgepodge of little mini units that we're going to go through briefly and then do quizzes on. All right, so it's a very chill unit, all things considered. This first part of it, though, is relatively important. It shows up a fair bit on the AP exam. And this unit is, this mini part of Unit 9 is called chi-squared for goodness of fit. And when we do chi-squared for goodness of fit, we're using what's called a chi-squared distribution. So just so we can visualize that here, I'm going to do a little graph. A chi-squared goodness of fit distribution is based on this idea of always positive values. So it's always going to be positive, a chi-squared distribution. Always, always, always. There are negative numbers never in a chi-squared distribution. And the reason for that is it's called a chi-squared distribution. What that means is we take every difference, as we'll soon see, and we square that value. And this is the letter or the value chi. And the way you calculate a chi-squared distribution is actually kind of cool. It's not even that difficult, I would say. It's the sum, right? Really ugly symbol, but the sum of an observed value, so a value that you've seen in your sample of a particular thing, minus an expected value, a value that is being claimed outside of your sample as the truth. You square that, because it's chi-squared, over the expected again. And what this does is it creates, by adding all of those differences together, the cumulative difference between a set of claimed values and the values you're observing in a sample. Something you should note is that this is specifically for proportions, and it's normally for many proportions. Which is to say you will have a bunch of different proportions in a single sample, and then you will compare how each of those proportions, the observed ones, right? How each of the observed proportions compares to the expected values that are given, right? And as with many of these tests, the proportions will be important as a statement, but you also will use the X's, right? The number of successes that you note, and that will be compared here. And what does a chi-squared distribution look like? I will do that in black. It is very right-skewed. It is a right-skewed distribution. And as degrees of freedom go up, it becomes more normal. Now, what is a degree of freedom in terms of a chi-squared distribution? Normally, it's the sample size minus 1. But for chi-squared, degrees of freedom will equal k minus 1. And k, in this particular case, this instance, is the number of categories. Now, all of this background information is present in your slideshow, so you can take a look at that on your own terms. What I want to spend the majority of this video doing is just working my way through an example chi-squared problem and showing you how we will use phantoms to solve it, because we will use phantoms to solve it, which is wonderful. We're repeating our acronyms, makes our life just that much easier. Okay. Now, before we go into any further detail, I want to make sure I've given you all the ideas I want you to have. So be aware, lower degrees of freedom on a chi-squared distribution are more right-skewed. As we go higher in degrees of freedom, they become more approximately normal. All chi-squared values are positive. And we use chi-squared specifically for multiple proportions within a sample, and we want to compare it between one set of values and another. I think that's everything we need. So let's rock and roll if we might, okay? Let's take a look at this example problem. I'm going to read it out loud really quickly. There's a candy company, and they have fruit-flavored candies. And there are 5 flavors, cherry, lemon, orange, apple, and grape. And the company claims that they have an equal amount of each of these flavors in any bag given, right? So we randomly select a bag of 100 candies, and we count the number of each flavor, right? And so we go through and we find our observed counts, right? So if we take a look, let's presume the assumption, right? We're going to take a look at the null that we are given. And the null that we're given, the value that we will use when we set up our hypothesis, first, I should say, before we set up our hypothesis, we'll look at our parameter. Now, you can either voice this parameter on your own, or as it says on the slideshow, you can put all of the context into your hypotheses. But for the sake of argument, the parameter we're looking at is we are testing whether the proportion of each candy flavor is equal to 20%, right? Because that was the claim, is that there's a 1 in 5 chance of each flavor. They are all equitable out of 5 flavors, and that amounts to a 20% chance, right? So that's what we're testing. That's our interest here. And so when we move on to our hypothesis, the way we would state it is our null hypothesis. You could say this several different ways, right? But one of the ways to say it is just the claimed distribution, and this is where you can put context, of candies or of candy flavors is correct. And another thing you could potentially add, if you want to be extra clear, right, is you could say each flavor appears with a probability of 0.2, right? That's just to give more context or background. And then, of course, our alternate is going to be that that's not the case. The distribution of flavors is not uniform at 0.2 probability per flavor. Now, you don't have to write all of that, but again, these are the clear ideas that you need to be pushing forward so that we're honestly aware of what our situation is, right? So we're giving background, we're making clear what our parameter is, and then we're stating our null and our alternate hypotheses just to make it clear, all right? And the null will always be, as it says in the slideshow, the claim distribution is correct and the claim distribution is not correct, right? Those are your two options. All right, we've done our P and we've done our H. Now we're going to hit our assumptions, okay? First one, random. It should say in the question. Must be stated. Okay? Always the case. Second thing, independence. What do we do for independence? Well, we're going to take our sample size, which in this case was 100. Right? But the key here to recognize is in our sample, we need to be like, well, that times 10 should be less than all candies, right? And we can make that particular assumption. Let me make sure this is clear. That's not a C, that's a less than. Okay, so we've got randomness. It's the same check we always have, and we have independence. Again, the same check we always have. We need also, though, one more thing called expected counts. Now, you do not have to call it expected counts, heroes. You can just write out what I'm about to write. You don't have to tie it to anything. But if you want to know, it's called expected counts. This is the equivalent of normal, but we're not looking for a normal distribution. We're looking for a chi-squared distribution, right? So we're looking for expected counts, proof that it's okay. Each flavor we expect will show up 20 times. So what we're going to do is we do n times p, right? And we check that that is greater than or equal to 5. Just 5 for expected counts. What that means in our case is our sample size is 100. We're going to then multiply that by the probability, right? In this case, the probability for our null was 0.2, and that's what we'll do. That has to be greater than or equal to 5. And indeed it is, so we're good to go. In class, for some of you, we kind of zoomed past this, so I really wanted to close connect this and make sure we were super clear on it. So you're going to take the sample size of your sample and use that in tandem with the proportion or the probability presented from your null, right, from your claimed values or expected values. Keep that in mind and be aware you don't have to do any checks for the sample proportions in this case. All right, we've met all of our assumptions. We get to the easy part now. We name the test. This is the easiest thing. What is this? This is a chi-square goodness of fit test. That is what it is. It's a chi-squared goodness of fit test. Check-a-rooney. We're good to go on that. Now it's time for T. And as you might note, T and O, we often combine together. Here's what I want you to know. For T and O, I'm going to put them together actually. For T and O, the T aspect would be, if we did this by hand, you'll remember, I showed you this is the formula for doing T. Here's how you get the critical value, the test statistic in this case. Observed minus expected squared over expected. And we would sum all those together. Now, you're not going to have to do that by hand. Okay, we have a calculator function for it. But be aware that gives you your chi test statistic. And so with that chi test statistic, as it were, we then would go in, and for the O, which is very important, you would go in and you would be able to do your chi test statistic using chi-squared CDF. Okay, because remember, we're not using norm CDF. So the one change here is, and you should be used to this by now, anytime you have a test statistic, find that test statistic's cumulative distribution function, CDF. We've done norm CDF for z-scores. We've done t-CDF for t-scores. Now we have a chi-squared score. So we'll use chi-squared CDF. And you will always make the chi-squared the lower. Why? Because this is always a distribution that moves to the positive, so we're always going to be looking at the right tail for a chi-squared distribution. Makes it easier. Upper will be 100,000. And then we just have to put the degrees of freedom, which again are the number of categories minus 1. So in this case, we had 5 categories. Our degrees of freedom will equal 5 minus 1, which is 4. Okay, now let me show you how to put it in the calculator. And this part is a wonderful part. So grab your calculators. And now we are going to make good use of those lovely calculators. I had to stand up and grab my calculator myself as well. So you are not alone, legends, heroes, friends. We are going to make good use of this situation. First things first, turn on your calculator and go to Stat. Now, as you notice, we have raw data here, so you've probably guessed it. You're going to want to fill up L1 and L2. So let's do that. Click Enter for Edit, okay? L1 should be, and this is super, super important, right? L1, you should put your observed data in. And the reason why is the way that it populates on your chi-squared distribution calculator, L1 tends to get populated in the observed category. So observed is what you saw in your data. If we scroll up for a second, it looks like 28, 22, 18, 15, and 17 are our values that we're using for our observed data. That's what we saw in our sample. So I'm going to go ahead and clear my L1 in case it's not clear, right? And then I'll do 28, enter, 22, enter, 18, enter, 15, enter, and 17, enter. Now your L1 should be populated with your observed data. We're going to clear L2 in case it's not already cleared. And then in L2, we're going to put our expected values. Our expected in this case was just 20 for each one. And the reason it's 20 for each category is because 20 is 20% of 100. So now we've got L2, and I'll just put this here, this is for our T still. L1, I would recommend that has your observed. And L2, I would recommend has your expected, right? So expected being the ones claimed. So we have our observed, we have our expected. What you're then going to do is you're going to Stat. Tests, you know this process. I feel like you already know where we're going. You go all the way down to D. Do not go to C, go to D. That says chi-squared. You want the one that says GOF test, not just regular chi-squared. Chi-squared goodness of fit. I almost said goodness of freedom. And is there any gooder than freedom? I think not. Goodness of fit test. You'll click enter. You'll notice it says observed and expected, and the L1 and L2 should match up. Then you'll have DF, our degrees of freedom, again, are 5 minus 1 or 4 in this case. So put 4 in. And you will click calculate. Now what you will notice is you get a chi-squared score, a critical value here. 5.3. That's important. Note that. You will then notice we have a p-value, that is the p beneath. The p-value is equal in this case to 0.26-ish, okay? You will need that as well. And then of course it states your degrees of freedom again, degrees of freedom equal 4. You should state that in your problem or your solution or however you go about it. Now of course you input those, but there you go. So we now have our solution, the last part, and the part that you probably know is coming already. We've gone through the phantom. Now we need the MS. And what is the MS? Well, it's what it always has been, M/S. We're going to do our p-value. We're going to compare that p-value to the alpha. In this case, right, here's what I would write. My p-value is equal to 0.26. That is greater than my alpha, which will be 0.05 unless I'm told otherwise, right? Oop. I'm realizing my 6 is pretty hideous there. Let's fix that up. Therefore, because my p-value is greater, right, I must fail to reject the null, right? In other words, there is convincing, or there is, I should say, sadly, I wish this weren't the case. I wish we could fight the power, but there is no convincing evidence for, in this case, there being a difference from the claimed values. So the rules hold the same. Now, if our p-value were under 5% or whatever the claimed alpha was, then we would say, hey, there is enough evidence that my values are different enough, right? So the bigger the chi-squared value is, the more difference there is between the data you got and the data that is provided as the claimed data, and therefore evidence of what you expect. Now, I want you to notice the M and the S are exactly what you should expect from this class, right? All of this should make very, very good sense. Remember that your chi-squared statistic is 0 or greater, always. Your chi-squared stat is always 0 or greater. It's positive, right? Remember also that as degrees of freedom go up, chi-squared becomes more normal, less skewed. As degrees of freedom go down, chi-squared stays relatively right skewed. And something that you should be aware of is that the chi-squared distribution always has at least a tiny right skew. If you go very, very, very big, you get almost exactly normal, and we can treat them as normal, but there's always a slight right skew. So always a slight right skew to the chi-squared distribution. So those are 2 points I want to hammer home. Okay, and the phantom should sit in place with you, right? Say your parameter, run your null and your alt, your null being that the distribution claimed is correct, the alt being that the distribution claimed is not correct. Be sure there is clarity on what the parameter is that you're messing with and that there is context. Then you'll give your assumptions, random and independent, the same as you've always had and in the same ways you've always had. But you'll do a check for expected counts instead of for normalcy, which is just where n, your sample size, times p, the probability of your expected value, should be greater than or equal to 5. You'll name your test, chi-squared goodness of fit test. And then your T and your O should be used to effectively calculate your chi-squared test statistic and then to determine the p-value. Be aware that sometimes they will give you a chi-squared test statistic and you have to by hand, or using your calculator, I should say, find your p-value, and that's when you use this chi-squared CDF. Otherwise, you should use stat tests and then chi-squared GOF test, and then you'll plug in your values. Remember, degrees of freedom are the number of categories, not the number of values when it comes to chi-squared. So for chi-squared, and only for chi-squared, degrees of freedom are number of categories minus 1, and then you will get your output. The p-value must, of course, be less than your alpha if you intend to reject the null and find convincing evidence for the alternate. But in this case, the p-value was greater than the alpha, so we failed to reject the null and find no convincing evidence for the alternate. I am proud of you. I can't believe we've gotten through as much as we have, but at the same time, I shouldn't doubt it. You are brilliant and you are capable. Remember that chi-squared statistics are always positive and that chi-squared data distributions are always slightly right skew, even at high degrees of freedom. Okay? But they do get more and more normal as those degrees of freedom go up. I am proud of you. I'm thankful to be your teacher. And this is Mr. Mays signing off.